here's a real head scratcher for you. How can a gigantic steel ship weighing thousands of tons float so easily, but a tiny little iron nail sinks straight to the bottom? Well, in this explainer, we're going to pull back the curtain on the invisible force that makes it all happen.
All right, let's dive right in. Here's our plan. We're going to start with that mysterious upward push you feel in water, figure out how to actually measure it, and then unpack the genius principles that let us build everything from huge ships to super precise scientific instruments. So, first up, we're tackling the big mystery itself. Why do things seem to get lighter in water? And how on earth can something so heavy float while something so small just sinks like a rock? Exactly this. It's the same material, right? Iron. But one disappears into the depths in a second, while the other can carry cars and cargo across entire oceans. It's not magic, I promise. It's an incredible, invisible force that we're about to get to know. And you know what? You can actually feel this force for yourself. It's super easy. The next time you see a bucket of water, just take an empty plastic bottle, seal it, and try to push it underwater. You'll feel it fighting you, won't you? That's the water pushing back, and it's surprisingly strong. Okay, so you fought against that force and you've got the bottle completely underwater. Now, what happens the very instant you let go? Yep, you guessed it. It shoots right back up to the surface. And that upward push, that force, has a name. It's called the buoyant force. As you can see, it's the upward force that a fluid puts on an object. And that word fluid is really key here. It's not just water. It applies to any liquid and even gases. It's the exact same reason a helium balloon floats up through the air.
Okay, so we know this force is real. We can literally feel it. But in science, feeling isn't enough. We need to measure things. So how do we actually put a number on this invisible push? Well, it's actually way easier than you might think. All you need is a spring balance. First, we just weigh something, like this stone, in the air to find out its real weight. Then we do it again, but this time with the stone completely underwater. And look at that. The reading on the scale actually goes down. The object seems like it lost weight, but it didn't. That difference is just the buoyant force helping to lift it up. Now, here's the really cool part. That lost weight is not lost at all. The difference between the object's weight in the air and its weight in the water, that number is exactly equal to the buoyant force pushing up on it. So for our stone, the buoyant force is a solid 2 newtons. All right, so we can measure it. That's a huge step. But what actually determines how strong that buoyant force is? What makes it push up harder or softer? Let's do a little investigation. A great question for any scientist to ask is, does the type of liquid even matter? I mean, if we took that same stone and dunked in salt water, or maybe glycerin, would the buoyant force still be 2 newtons? What do you think? And the experiment gives us a really clear answer. Nope, not at all. We use the same weight every time, but as you can see, it experiences a different buoyant force in each liquid. Just remember, that loss of weight column is the buoyant force. It's clearly strongest in glycerin and weakest in plain water. And here's the aha moment that explains why. When you look at the densities of these liquids, you see a perfect pattern. Glycerin is the densest liquid on this chart. And guess what? It also gave us the biggest buoyant force. So the rule is simple. The denser the fluid, the stronger its upward push. So let's just boil this all down. The strength of that upward push really depends on 2 main things. First, as we just saw, the density of the fluid it's in. Denser fluids just push harder. And second, the volume of the object that's actually in the fluid. The more space you take up underwater, the more water you're shoving out of the way, and so the harder that water is going to shove back. And, this whole idea, this connection between an object, a fluid, and a force, it actually takes us on a little trip back in time, more than 2,000 years ago, to one of the most famous eureka moments in all of science. So the story goes that the brilliant Greek scientist Archimedes was trying to solve a tricky problem for his king, and he figured it all out while getting into his bathtub. He noticed the water level rise and realized that when you put something in water, it pushes away, or displaces, a volume of water that's exactly equal to its own volume. And that simple bath led to his incredible, world-changing discovery, Archimedes' principle. It's so elegant. It just says that the buoyant force pushing up on an object is exactly equal to the weight of the fluid that object pushed aside. Remember our spring scale experiment? That weight that seemed to disappear? It wasn't gone. It was just the weight of the water that our stone displaced. Mind-blowing, right? Okay, so now that we have Archimedes' principle, we have the final key. This is the ultimate tool that lets us understand once and for all why some things float and other things sink. The principle of flotation is basically a balancing act. For anything to float, it has to sink just enough to push aside a weight of fluid that's exactly equal to its own total weight. At that point, the upward buoyant force perfectly balances the downward pull of gravity, and it just hangs out there, floating. You can see this for yourself with a little piece of aluminum foil. If you shape it like a boat, it floats no problem. Why? Because that boat shape has a really big volume. It's able to displace a lot of water, enough to match its own weight, which creates a strong buoyant force that keeps it afloat.
But if you take that exact same piece of foil and just crush it into a tiny ball, it sinks instantly. It's the same weight, same material. The only thing you changed was its shape, which changed its volume. As a little ball, it's just too small to displace enough water to equal its own weight. And that is the solution to our ship and nail mystery. A ship is mostly hollow inside. Its huge shape displaces a massive amount of water, creating a powerful buoyant force, while the tiny solid nail just can't. Now, this isn't just a neat science puzzle. These principles of buoyancy and flotation are the basis for some really important tools that we use in science and industry every single day. For example, take a look at the hydrometer. This clever little device is pure Archimedes in action. It's designed so that it floats at different heights depending on the density of the liquid you put it in. In a less dense liquid, it has to sink lower to displace enough weight to float. In a denser liquid, it bobs up higher. The scale on its side lets you read the relative density right off the instrument. It's genius. And that brings us to one last challenge for you. Take a look at this. In the air, the object weighs 50 newtons. As it goes into the water, the reading drops to 40, then 30. So what's the final reading on the spring balance going to be? But more importantly, can you explain why using everything we've just learned about Archimedes' principle? Give it a shot.